No, don't need any add-ons, just base Excel itself. I might later in the semester show you how to use Solver, but that's an edge case, and if we do get to that, there's going to be a lot of time. So homework 2 is available now on Blackboard, and you should be able to make real good progress on that after today's class. Actually, we will have covered everything that's included on homework 2. So it's before class on Wednesday that homework 2 is due. I believe that the grader has already finished homework 1. Was everybody able to see the feedback there? The grader, I've asked to write little comments on any of the problems that you've got wrong, so that if you have anything other than a perfect score, then you can see how many points were taken off for which problem and why. I trust the grader. It's a really great student who I think will do a good job. But if you think there's a mistake, if the grader has made an error, or if you think the scoring is unjustified, if you have any concern, let me know, because ultimately the responsibility is mine to make sure that your work is evaluated correctly, and I want you to get the points that you deserve. So if you think there's been a mistake, then let me know and I'll address it. We're going to continue talking about cash flow diagrams today. Just remind ourselves the convention for a couple of types of cash flow diagrams. Then we're going to talk about gradients, which is a little bit of a more complicated type arrangement that will lead us into some complex real-world cash flow diagrams next week. Okay, so to revisit the find P given A cash flow diagram, the thing I wanted to emphasize is that the lump sum present value is 1 year before any of the annual series are seen. So if you also had some amount at time 0, so like if there was an error, an arrow up at time 0 that was the same length as the rest of them, then that wouldn't count as part of the annual series. So let's just say that there was, you're getting whatever this amount is. If it's $100, if you're getting $100 at 0, 1, 2, 3, 4, 5, well, the find P given A still would only have an N of 5, even though there's 1, 2, 3, 4, 5, and 6 arrows. The arrow that's at time 0, if there was one, it wouldn't count as part of the annual series. That would be some amount that's already at the present and not included in the annual series. So the point I'm making is that the annual series begins 1 year after the present, that the cash flow amounts should be equal amounts, they should be consecutive, and then this standard factor notation is also something that we talked about in a prior class. Putting in parentheses how we're defining the problem statement. So this parentheses of P/A, that means that this is the problem type where we want to find P given A at some interest rate and some N value. And what's in parentheses there, as you're writing the problem out, you could then substitute in the actual factor that you looked up off of the table. So if you went to the column that was the P/A column for a certain interest rate and then found the row associated with the N value here, so this is N equals 5, then you'd simply take the factor, multiply it by A, and then that's the lump sum equivalent value at P. So wait, what are we even doing? Just to take a step back, like what is this even all about? This is about economic equivalence. This is saying we want to find out the amount at the present that is economically equivalent to this annual series. So it's not the same number of total dollars. It'll be fewer dollars at the present, but it's economically equivalent when the future amounts are discounted at the interest rate that applies. So if you have the reverse of that and P is given and you want to find the annual equivalent, the same thing is true where it's staggered by a year. The first arrow that's a component of the annual series is 1 year after the present. So P is before the first annual amount. So any questions about the P and A type cash flow diagrams. Now, future and annual are also a little bit unusual because by convention, the lump sum future value exists in the same year as the last A. And then again, we don't have anything in time 0. So if you ever have a cash flow diagram where there is some amount in 0, and I ask you to find the future value of all of it, you'd have 2 steps you'd have to do. You'd first have to take this annual series to times 5, to time 5, and then separately from that, you'd have to take whatever amount is at 0 to year 5. So the point is that the annual series doesn't include time 0, but the future value is assumed to be in the same year that you have the last part of the annual series. So again, the arrow lengths are the same because for it to be an annual series, the amounts have to be equal. And if you have F as the lump sum known and you're trying to find the annual equivalent, then all we do is we'd go to a different column in the factor table to look up what factor should be multiplied by the F in order to find A. But look how it's reversed. If you're finding F given A, then you use the F/A factor. If you're finding A with a known F, then it's A/F, which is the opposite of that other one. Any questions about this review of cash flow diagrams? Yeah.
What if in our homework, for example, the present worth arrow and the A arrows are both pointing upward?
And then are you finding a future or are you finding
You'd be finding the present value.
Then you'd add together the present equivalent of the A's to the amount that's already at time 0. You just combine them.
Okay.
Other questions? Okay. So let's say, just as an illustration, an industrial engineer made a modification to a chip manufacturing process that will save her company $10,000 each year compared to previous expenses. So is that an inflow or an outflow? If you're saving money, that means you're shelling out money to save it, right? Is that what the word save means here? Like putting it into an account? This is kind of a special case. Do you remember I told you about this special case of how previous expenses you used to incur, if they're avoided, then that actually counts as an inflow. So this is one of those. Previously, they used to spend some extra money, but the engineer has made some modifications that has reduced the expenses. So we treat that as an inflow. $10,000 each year compared to previous expenses. So if we're going to draw a cash flow diagram of this, what it's saying is we've got 7 years of those savings, each of which are $10,000. So 1, 2, 3, 4, 5, 6, 7. Amount is 10,000. And again, the reason why the arrow is up is this isn't save like you're putting the money into a savings account. You're not shelling out money. This is expenses. It's not a deposit, but it still counts as an inflow because it's what you previously were spending. So we want to find out what's the equivalent lump sum value in year 7. So we want to say, instead of all of this spread out over time with interest rate of 8%, how much would it be if it was one big lump sum value in year 7? So this is find F given A, I equals 8%, N equals 7. So that's how I'd write it in parentheses. This shorthand notation, find F given A, I equals 8%, N equals 7. So here's my 8% table, and here's the F/A column. That's convenient. So the factor that is with this n equals 7, 8.9228. So what goes inside here is just the 8.9228. That's the result of this. Like the find f given a for 8% n equals 7 is this number, the factor. And then I'm going to multiply that by the amount of 10,000 to find the lump sum future value. Because this is the A. And if I multiply the actual numerical amount by the ratio that tells me the future equivalent, then that'll tell us it's 89,228. And so just to revisit the idea of precision and the number of significant digits here. So our factor had 1, 2, 3, 4, 5 digits. And so my answer should have 5 digits as well. So 1, 2, 3, 4, 5. 89,228. So I'd round off to the nearest dollar. So that's a good kind of refresher of how we convert what's inside the parentheses, this kind of like standard summary of the problem type and the parameters, into a factor that then we multiply by the known A. Any questions before we move on from this one? Okay. Let's say you had a motorcycle and this year spent $100 to maintain it. And then next year you also spent $100 to maintain it. But then, as all things do, it starts breaking down a little bit more often. So in year 2, you spend $200 to maintain it. In year 3, you had to spend $300 to maintain it. Year 4, you spend $400 to maintain it. You get the idea that the amount is going up over time. And so there are real-world illustrations of where, amounts aren't always an annual series that's constant. It could be that somehow the amount is increasing with a known regular amount. And this is a gradient. This is an illustration of a gradient. So as a cash flow diagram, this is what a gradient looks like in its simplest form. In its simplest form, times 0, or the present, we don't have anything of the gradient. But if we were going to find the lump sum present value, that's where we'd put it, is at times 0. Now, gradients are a little bit weird because you don't see the effect of the gradient in year 1. In year 1, it's like 0 times whatever the gradient amount is. And so if the gradient amount is $100, there wouldn't be anything in year 1 that's extra. But then the increment, the added annual increment, begins to manifest itself in year 2. So in year 2, year 3, year 4, it's increasing by a fixed amount every year. So this illustration that I did here, the amount of the gradient is $100. But there was also like a base of an annual series that this gradient is being added on top of. But the gradient component of it is just that year 2 is the first time that you start to see the regular increases. And then each subsequent year, it's going up by the same amount. So this standard notation, if you wanted to find the lump sum present equivalent of that, you'd multiply it by the gradient value, and then you'd simply go to the column in the factor table or use the equation method. If you look at the handout of formulas that I gave you previously, there is a P/G row on those equations. Just like, all of these equations have been solved for different n values and different interest rates in the factor tables. You could make your own factor tables using these equations. That would be a fun weekend activity since we got, the holiday coming up. You can make your own factor tables. Or not, I don't know. But the point is that you can use the equations here, find out what the factor is, because sometimes you'll have an interest rate like 2.37%. And there's no factor table for 2.37%. So like on an exam, I wouldn't necessarily tell you in every case if you have to use the equation method or the factor table. But if you don't have the interest rate provided, then that kind of implies you're going to have to use the equation method. So the takeaway points, in terms of the form of gradients is that you start to see the impact of the gradient in year 2, just by convention, not at the end of year 1. So by the way, sometimes time is hard to understand. So when I talk about the first year, I'm talking about a length of time. The first year starts at 0 and ends at 1. So that distance between 0 and 1 is the first year. So time 1 is just an instant. It is that where the mark is. The 1 is just an instant in time. But like the second year is a period of time between 1 and 2. And then time 2 would be right at the point. So when you're reading word problems here, when it talks about the first year, the second year, keep in mind that that's talking about a period, not necessarily an instant in time. Yeah.
So the instants on time on the cash flow diagrams, those are like, so where it says year 1, that's the end of year 1. And then where it says year 2, the number 2 would be the end of the period of year 2.
That's right.
Okay.
Yeah. And remember, the end of period assumption is that unless you hear otherwise, we're going to assume that all of the inflows and the outflows that occur during a year are kind of like expressed at the end of that period. So like the arrow in a cash flow diagram, it's just, you know, maybe there were some transactions that occurred during the year, but we do the full accounting and show the up or down net of that at the end of the period. That's the end of period assumption. So again, I'll emphasize the point that the present value of the gradient, if you're finding the present value, is 2 periods ahead before the first time that you see G. Because in year 1, it's 0G. 0G, 1G, 2G, 3G, so on. So what about this? What are we seeing here? Is this a gradient or an annual series? It's both. It's a gradient on top of an annual series. So the annual series, like the way, I wish I could draw on this screen, but I've learned my lesson on that. Let's just assume that there's, you know, that these arrows go all the way for the annual series. And so it's an annual series that starts here at, you know, you see the first at year 1, so time 0 is here. But then the gradient, we don't actually see it until this year 4. So if we did a find P given G on the gradient component of that, it would take it to the lump sum present value to year 2. So we're going to start talking next week about like quasi presence. You know, like if we want to find the present value of this, then it would be kind of multiple steps to do it. But I wanted to point out that it's not always going to be as clean as just like only a gradient or only an annual series. Often it would be like a combination of the two, and then maybe some lump sum future values thrown in there as well. So the gradient can kick in any time in the future. It doesn't always have to be just in year 2. It's still a gradient regardless of when it begins. And then a gradient can be combined with an annual series. All right, let me hand out these in-class exercise papers. We've got some good practice lined up for today.
quicker if you want. That issue, I didn't either. I saw your car still there, and I was like, okay, maybe it is quicker.
If I can interrupt just briefly, let's look at 1 and 2 together, and then I'll give you some more time on problem 3, just to make sure we're all on the same page with the first problem. So you give a $7,500 loan at 8% interest, and the loan should be repaid in equal annual amounts over 8 years. How much should each annual repayment be? So that's find A given P, I equals 8%, N equals 8. That's how we summarize this problem type. And going up to the table, find the A/P, that's called the capital recovery column, and then go down to the row that's associated with N equals 8. And by the way, this is the 8% table. So 0.17401 multiplied by 7,500. And when I did the calculations, I got $13.05 and 8 cents. But I've only got 5 significant digits in my factor, so that's why I rounded the final answer to the nearest 10 cents, is because the final answer should have 5 significant digits as well. 1, 2, 3, 4, 5. All right, so any questions about the first one? All right, on the second problem, the first thing I asked you to do is write the years on the cash flow diagram. You'll notice that there was no years on the horizontal axis, and that's intentional because I wanted you to think about what is year 0, what is year 1, when are you seeing the first evidence of a gradient? You're seeing it in year 2, and that happens to coincide with like the definition, the base definition of a gradient is that it's 2 years after time 0. So here, the time 0 from the perspective of the gradient coincides with actual time 0. There isn't a separate like quasi time 0 like we'll get to next week, but the actual time 0 aligns with 2 periods prior to the first evidence of the gradient. Okay, so I wrote the years on the cash flow diagram. Based on that, N equals 4, because the N for a gradient isn't how many arrows there are. The N for the gradient is what year is the last amount of the gradient. So the last amount of the gradient was in year 4, so that means N equals 4. So it's important to point out, it's not necessarily the same number of arrows, the N value. Okay, find the present value. So if we go to the P/G column in the table, P/G, find P given the gradient. I equals 8%, N equals 4. We can look up the factor, and it's 4.6501. Multiply that by 200. So the lump sum present value, the economic equivalent present value to this gradient is $930 at time 0 is economically equivalent to this series of inflows in years 2, 3, and 4. They're economically equivalent. Okay, then the last part here, part D, find the future value in year 4 using the equation. The F/G equation is a beauty. So remember, my recommendation is don't just do this whole thing in your calculator. That's just a recipe for calculation errors. You can't afford to make mistakes. So you write the equation, then make the substitutions, showing, like what did you put in for N, what did you put in for I. And then you can see I've done some intermediate calculations here, like with this bracket here where I'm saying the result of this first component is 56.3264, the result of the second component is 50, and so on. So show the steps. The more steps, the better. It's just less likely that you're going to make mistakes. And when you do make them, it's more likely that you'll identify and be able to correct them if you've written out your work in good detail. So the final answer for part D should be $12.65 and 28 cents. Anybody else get that same value for part D? Okay, good. All right, so I'll cool down again. I'll stop talking, give you a chance to continue working on problem 3. Okay, so part 3, we've got this cash flow diagram that's an annual series and a gradient. Both of them are there. So if you split off, like just make 2 different drawings, then it's going to look like, here's an annual series where the A is 400, and then there's also a gradient where G is 30. So just find the present value of those 2 parts and then add them together.
It's so clean there.
37 cents off.
I really
All right, so for this last problem, we want to find the value of the annual series and the value of the gradient. So first things, if I find the present worth of the annual series, P/A, make all the substitutions and so on, it should be $14.41.91. That's the present value of the annual series. And then the present value of the gradient, we plug through all these calculations and so on. It's going to be $191.91. So altogether, the combined present value is $1633.82. All right. This thing I drew on the board over here, just kind of a what if. I got a really good question as I was walking around. Somebody asked, you know, does a gradient have to be the same amount every year? And the answer is yes. That's the definition of a gradient. So if you see something that kind of looks like it's a gradient, but the amounts aren't exactly, if it's not like linear, then that's not a gradient. Then the way that you'd have to find the present value there is just treat each of these as individual future amounts, which you discount to the present. There's not some kind of like shortcut approach as we've been learning for the rest of this.
Yeah, it has to be like a uniform gradient.
That's right. Okay, we're out of time. I can stick around if you've got individual questions. The next homework assignment is due before class on Wednesday. We won't have class on Monday. See you Wednesday.